Miss Parent here with you one more time to help you figure out how you can determine how fast an object is traveling in orbit. Now this is a nice question because one, it combines gravity and circles, and two, they may very well ask you how to derive this equation on the exam. And so if you don't know where to start, my suggestion always is, when in doubt, free body diagram it out. And so the question I have to ask myself is if this is a planet with mass big M, and this is a little planet in orbit around it, or like a moon, and they're separated by an orbital distance of r, which would be center to center, what force is acting on the little m to keep it moving in circular motion around the big planet? Well, that would be, of course, the force of gravity, or F big G. And what I know about F big G, or Newton's law of gravitation, is that it is given by some constant G times the big M times the little m all over the distance between the two squared. Now I also know that because this little moon is in circular motion around the planet, that F net equals mac because I'm moving in a circle. F net is helping minus hindering. Well, the only force acting on the moon right now is that F big G, and so that is my F net. And so I end up with F big G is equal to mv squared over r. Now F big G is also equal to this term right here. So I'm going to take this and I'm going to plug it in for Fg and set it equal to mv squared over r. So I get big G, big M, little m over r squared is equal to little m v squared over r. Now it's important to understand why it's the little m that I put here and not the big M. And the question I always ask myself about which m belongs here next to the A is it's whatever mass is doing the orbiting. And so since my moon is orbiting the planet, that is the mass that's undergoing the centripetal acceleration. Therefore, it's the little m that I place here. Now I want to solve for speed, how fast. That means I need to multiply both sides by r. And when I multiply both sides by r, I notice that I get to drop or cancel some r's out. And then I'm also going to divide by little m, not big M, but little m. And when I divide by little m, the mass of the moon or satellite or whatever's in orbit drops out of my equation. And so I'm left with v squared is equal to big G, big M over r. And so the last step would be to take the square root. And so that would be this v is equal to the square root of big G, big M over r. Now that's the equation right here of an object that's of the speed of an object that's in orbit. Something to remember, this m here is the mass of whatever is being orbited. So this is not the mass of the satellite, not satellite or moon mass, not, but mass of planet. Now that could be planet Earth, it could be Mars, it could be some other planet, who knows. But it's whatever is being orbited, that's what that mass is. Okay, so just don't get confused there. The other way that they could have you determine the speed of an object in orbit is using the period. Okay, and the fact that v is distance over time, speed is distance over time, And the distance that the object travels when it's in a circular orbit would be the circumference. So that would be 2 pi r over t. And so this equation here is also very useful. This would be the speed. T here would be the period of the orbit, or the time for one complete loop. One complete loop around the planet, and r would be your orbital radius. And if you know these equations, then you can calculate how fast an object's traveling in orbit. Again, it doesn't depend on the satellite or the moon's mass, but it does depend on the mass of the object that is being orbited and how far away you are from that object.